time ever. As a whole, there are 50 plus competitions, virtual tech exhibitions, project expo, and guest lectures. I'm even proud to say that our Teckzite team is contributing 20% of the registration fee for the medical advancements which is needed in this unusual situation. And today, I take the privilege to introduce our speaker, Professor Thalappil Pradeep. He is an institute professor and professor of chemistry in the Department of Chemistry at Indian Institute of Technology, Madras. He is also the Deepak Parekh Chair Professor. In 2020, he received the Padma Shri Award for his distinguished work in the field of science and technology. He has received the Nikkei Asia Prize in 2020, the World Academy of Sciences Prize in 2018, and the Shanti Swarup Bhatnagar Prize for Science and Technology in 2008 by Council of Scientific and Industrial Research. We are really honored to have you joining us here to enlighten us for your thoughts, sir, with your thoughts, sir. And without any further delay, now I hand over the lead to Professor Thalappil Pradeep Garu. Thank you.
Can you please enable screen sharing? Ratnavali.
Sir?
Can you please enable screen sharing? Yeah,
yes,
okay.
Yes, sir, it is. Sir.
All right. Can you see this? Can you see the screen?
It is visible, sir. Yes, sir, it is visible.
Okay, I'm audible well, or is this some noise is there?
No, sir, everything is clear, sir. Please carry on.
Very nice. Well, it is always a pleasure to join an enthusiastic team of youngsters sharing one's own work. Today, I am sharing with you some work that we have been doing on clean water. The reason I chose to talk about this is because yours is a technical festival, and in case, well, this kind of an exposure should enable you to look at new possibilities in one of the mundane problems that faces humanity. So I chose to talk about water, and there can be very many. In fact, no effort is excess. Every effort matters in the context of clean water. In my institute, we not only do basic science, but also translate the science for the benefit of people. So for that, we have built several companies in our laboratory. We are in the process of building many more. We are in the process of contributing to many more built by others. So in case you are interested in, we can discuss this aspect further. May not be in this particular forum, maybe later on, because I will not be covering every aspect of basic science here in this lecture. This will be largely a tour through our science and its applications. One thing must be said right at the beginning. That is, our economic, social, and cultural outcomes, all of them can be traced to water. You know, when I say this, it's important to realize, let me just take the right pointer here. Any issue that you have can ultimately be traced to water or the lack of water. And one may say that water is the simplest and simultaneously the most complex problem It is a simple triatomic molecule, and we study that in different contexts in our lab as well as in many labs. Over 10,000 papers are written around water and many different aspects of it every year. So water continues to attract people in many different ways. Still, water is complex. And one may say that everything simplifies to water, meaning every problem simplifies to water. So that being such a large problem, and it is, I have written extensively. Of course, you will see many books in this area. But our concern today in this discussion is about clean water or drinking water. And in a recent article, we wrote this much, and so this will put things in perspective for many of you. Water scarcity affects over 40% of the global population. So we are not talking about small issues. And in fact, it affects almost everybody. About 2 billion people do not have access to safe water. We know this probably every day you hear about issues of this kind in the newspapers. Over 2.2 million people die every year due to multiple water quality issues. And they are microbial pollution, heavy metal contamination, or plastics or microplastics, many others. About 80% of wastewater goes into waterways without adequate treatment. And that causes additional problems for water. Over 200 million people are affected due to fluoride. And I don't have to tell you, people from Andhra Pradesh. 220 million due to arsenic. Several million people due to nitrate, calcium, and cadmium, chromium, perchlorate, and several others. Annual global mercury emissions from anthropogenic sources that amounts to 2,220 metric tons, causing contamination in air, water, and all that. So what this shows is that it is not just a collection of problems that we are supposed to face. It's also challenges for the engineering community to address, for the science to address, for scientists to address. It is also important to know that consuming water having low dose, that is less than 10 micrograms per liter of arsenic, for over 5 years can cause irreversible changes in people, resulting in hyperpigmentation, while chronic exposure impacts the reproductive system, heart, etc., and can even lead to cancer. So having said this, if you subject your own people to things of this kind, irreversible effects of this kind, for not because of their own action, just because they happen to live in an area, they happen to get exposed to contaminants of this kind, obviously the nation is subjecting people to irreversible damages. So therefore it is national interest, it is of national interest to address these challenges. Naturally, water is one of the major things addressed by sustainability or sustainable development goals of the United Nations. Clean water is one of the important sustainability goals, that is clean water and sanitation, number 6. But then it connects to every other goal. So if you look at climate action or life below water or life on land or social justice or any such issue, zero hunger and good health and quality education and gender equality, in all of these, water comes as a very important enabler. Or clean water is an important prerequisite to ensure that life on land is safe. So in the past several years, nearly about 21 years or so, we have been looking at water in many ways. And my science has been essentially, if I can summarize into one sentence, I have always been advocating the statement that affordable clean water is a problem of advanced materials. So if you have advanced materials, you could solve the problem of clean water. If you don't have them, affordability may not be there in clean water. So using many materials, we have created new adsorbents. We have created new sensors. We have created new catalysts. Globally, several phenomena have been discovered and been used in the context of clean water. Collectively, several new devices have come. And we have written about this also in various fora. But an important aspect that all of us have to understand is that nanomaterials have become atomically precise. It is not anymore of some particles which you can see under a microscope, and therefore you call it certain nanometers in diameter. This is all right, is important, but it is also important to understand that the chemistry, the properties have become, or the materials themselves have become atomically precise. So what do you mean by that? That is, nanoparticles have become so well defined that you can call them as a molecule. So for example, this is a molecule of a nanoparticle, or it's also a nanoparticle, but it is molecularly precise. With 25 atoms of gold and some ligands, 18 of them, with some charge. And this can be synthesized in the laboratory routinely. And you can characterize this in the laboratory routinely. Here is a clean material synthesized in the lab, and you measure something called a mass spectrum of this species, and you get really well-defined mass spectrum with so precise numbers like this. And once you have this, of course, you can synthesize, well, you synthesize it, you can crystallize it. And when you crystallize it, you can have single crystals, structures, and they look like this. And once you have this, you can put them into computers and ask the question as to what are the properties, like spectroscopic properties, chemical properties, physical properties. And you can study all of these with great detail. And this has happened on a large number of nanomaterials. It's not that this has been used in clean water, but this was only to illustrate the point that materials have become atomically precise. So you can study this in great detail. We have looked at such materials for their capacity to remove contaminants. Ultimately, there must be a use for it. So we created such materials, and we asked whether these can address real water challenges, real world challenges, problems of clean water. So here is a boy pumping water from using this called something called a cast iron pump. And this is about a 40-year-old pump. And it is pulling water from a depth of about 60 feet or so in a region in Nadia district in West Bengal. The water that is coming out has about 160 parts per billion, 160 micrograms per liter of arsenic. The limit of arsenic is 10 micrograms per liter, as I mentioned previously. So what you're getting out is contaminated water. And when this water comes out, it also comes along with some iron And iron, if it falls on this cement platform, it creates red stains, and you have seen such red stains routinely, and that is iron oxide stain. And if you see such a stain in this region, it is also indicative of the possibility of arsenic present in this water. As I mentioned, arsenic is present. People have been consuming this, and this problem is known for over 104 years or so globally. And in India, it is known for several tens of years. In this region, for over 40 years. But then it has, the problem is that affordable solutions are not implemented in the field. So using such materials as I just mentioned, we made a contraption of this kind with 7 kilograms of this material packed in it. And one stroke of this pump gives you 300 ml of water with no delay, no additional pressure drop, or no excess load on this buoy. So you get this water. What it means is that 3 strokes of this pump gives you 1 liter of water. And therefore, these kinds of units can be installed in every school. And in fact, it was implemented in every school in this district. So everyone gets clean water during the interval time. The basis of all this, such kind of, or I should also say that this gives you about 1,000 liters of water per day in a community. And the water can be there, or it can deliver water for over 1 year or 2 years, depending upon the concentration of arsenic present in this water. This filter can work for 2 years or 3 years, and then the filter medium has to be changed so that you have material, when it exhausts its capacity, that has to be replaced. So the basis of all this is something called green materials, or we call them as water positive materials. Water positive materials are materials wherein you require a certain amount of water for its production of the material, but in the course of its useful life, it produces several orders of magnitude larger quantity of water. So this is a water positive material. In the case of this material, we are talking about a water positivity is something of 10 to the power 3 times. 1 liter of water used for its production, you produce over 1,000 liters of clean water. So that is really exciting. In addition, these materials do not use electricity for their production. They don't recontaminate water. They also don't use organics, organic compounds or chemicals, routine chemicals for their synthesis. What you do is you create such materials that are porous, and you pass contaminated water through it, and you get clean water. The moment you say that you have nanoparticles or nanomaterials based water purification, people ask this question: do you release nanoparticles in water? You don't release nanoparticles, and this is studied with spectroscopy. So take, for example, some E. coli bacterium, and you deliberately supply nanoparticles into them, and they look like these. And take one particle, which is a bacterium here, and expand it, it looks like this. These are all nanoparticles inside this organism when the organism is exposed to nanoparticles in the solution. And you can do spectroscopy to see that these are all particles. But if these very same bacteria, if you pass them, or this may be E. coli, You pass them through your material. These materials break these organisms, and you see lysis, but there is no nanoparticle. So there is no nanotoxicity. Although you destroy the organisms, you don't have any nanotoxicity. So that is one class of materials. There are many, many different types of materials. So one such regular material that we create in the laboratory is called iron oxyhydroxide, what is called a two-line ferrihydride. The material that we produce in the laboratory is metastable, meaning that it is not the thermodynamically most stable form. But we can preserve this thermodynamically unstable form in the nanoscale. And such a material is very important because it picks up arsenic substantially. So what you see are transmission electron microscopic images. Synthesized material is nearly amorphous in structure. And a little later on, with electron beam irradiation, you see small grains of this kind appearing. And you ask this question, how big are they? They are less than a few nanometers, and they're highly ordered. And you ask various questions with several advanced tools of spectroscopy and microscopy, and you understand very many aspects of these materials. Now, what you see in this figure is that nanoscale materials can be engineered, and you can, in fact, keep metastable forms stable in synthetic conditions of the kind that we have employed. And we ask, can we use such materials for arsenic uptake by a number of spectroscopic techniques? You see two distinct kinds of spectroscopy. I do not want to spend time on this side. It's called photoelectron spectroscopy, but this side, you see Raman spectrum, the Raman spectra of during the adsorption of this arsenite and arsenate on these materials. Arsenite, for example, looks like this, and it has a well-defined Raman spectral features. And you can ask this question, if you start putting this material on the surface of iron oxyhydroxide, what kind of structures do you get? And if you put arsenate, that's the other form of arsenic, in water, called a valence state of 5 in water, it has well-defined features as well in the Raman spectrum. Now, when you put arsenate or arsenite onto this material, what kind of adsorbed states are there on this? And using this kind of adsorption or adsorbate structures and understanding what kind of specific species are present in water, it is possible to model an adsorption mechanism of arsenite and arsenate on this kind of materials. So using this, we develop several materials optimizing the adsorption capacity. Now, when you optimize this adsorption capacity, you see that here is a particle, and there are various kinds of sites on which you can adsorb arsenate or arsenite, and you can ask this question, how many arsenate or arsenite species can be removed by a model nanoparticle? And it is possible for you to increase that adsorption capacity better and better with this greater with greater insights from such studies. Why do you do this? Because you would like to study, you'd like to create materials having very large absorption capacity, specifically for ourselves. Take, for example, a small cartridge like this, wherein you put about 25 grams of this material, and you pass 200 parts per billion arsenate and arsenite containing water through this. And what comes out is arsenate and arsenite combined concentration less than 2 parts per billion. And through this, you can remove arsenate and arsenite for over 1,100 liters of water. And so you set this up in the form of a device. So here is a solution containing arsenate and arsenite as well as iron. Arsenate and arsenite are colorless. So this color is because of iron that is present in water, iron 3+, and you pass it and you get clean water. Now, as you can see, this is done with that kind of quantities, but you also run this experiment for several thousands of liters of water. What it means is that you can now take such products in the field. Now, there are several regions in the country, we have several villages in the country where this kind of plants exist. These plants are traditional plants with materials such as alumina absorbing arsenite and arsenate. A typical plant supplying water to about 2,000 people will be in an area of something like 40 cents of land area. And the material that is charged in here is something like 3 tons. And it supplies something like 20 meter cube per hour of water, or something like 200,000 liters of water every day. Now, this whole thing, because of this large capacities of these materials, etc., that I told you, you can shrink it to 3 cents of land area. And it is, input water is 168 parts per billion, and output is less than 2 parts per billion. The capacity is 18 meter cube per hour. Now, this kind of plants can be implemented in the field. And obviously, it has gone in many different regions of the country. Some are here arsenic affected, some are some other contaminants affected, etc. Smaller plants also have been implemented, many as I mentioned to you previously. So what does it really mean? What is important to understand is the economics. Clean water that I just mentioned to you is affordable, and the price of that is 2.1 paisa per liter. With all costs included, the capital costs, the maintenance costs, the replacement costs, all of them included, this is the kind of cost that you have. Now, this is not about one plant or something. These are implemented for several hundreds of plants of large magnitude that we are talking about in the past several years. So where is this going to? Well, such technologies can be implemented in the field along with a lot of sensors. So what it means ultimately will be that smart water purifiers will be available across the country and other parts of the world. So we have several of these sensors now. This is not from our lab, from several globally. And this can be smartphone-based sensors or electrical sensors or potentiometry, and many different kinds of methodologies exist. And these sensors can be deployed on water lines or water treatment plants, or it can be implemented at point of use. And globally, such sensors are now possible. I'll show you a brief 2 minutes movie to tell you what is going on today in the field. So here is, I hope this is going to play. Here. So what I just told you is that it is indeed possible that affordable clean water, free of contaminants, can be supplied to anyone, everywhere, across the country and elsewhere. All it needs, of course, is people to come together and look at advanced solutions. Now, this is about materials that we are implementing today, but there are many, many other advances. For example, atmospheric water harvesting is something that we do in the laboratory. So to create that, you need to have atmospheric water harvesters. So we create such harvesters by a process called electrospray. Electrospraying micro droplets containing metal ions, you can create nano brushes. So these are nano brushes that we create, similar to the brush that you will see on, let us say, cacti, thorns, or on grass. So in the morning, you see that these cacti, these thorns condense humidity. When the temperature goes below the dew point, water condenses out. These nano brushes similarly can condense humidity. So we create such structures in the laboratory similar to biomimicking as this organism would do in a desert. It's called as a desert beetle. Now, using such structures on a condensing surface, we can draw water, draw air with humidity, condense humidity on the surfaces, and collect water. We have a company on this supplying 100 liters of water or 400 liters of water or 2,000 liters of water every day. But globally, so this is about active cooling, but globally, there are several other efforts wherein cooling is really not required. All you have is advanced materials which are porous. They condense humidity in their pores and transfer that humidity to materials, other materials. And when this is in the night, and when sunlight comes on or sun comes on, the material which has water, it absorbs temperature or it absorbs heat and increases temperature. And in the process, a phase transition happens in this material, and the material becomes hydrophobic. It releases water, and thereby, in a night-day cycle, you can absorb water and release water sustainably. There are several other efforts too. You might have heard about two-dimensional materials. So molybdenum sulfide single sheet is such a two-dimensional material. We have found ways by which you can create holes in this molybdenum sulfide and nanoscale holes. And a molybdenum sulfide sheet will look like this in a transmission electron micrograph, and there can be holes of this kind. And these holes, if you look at them in great detail, they are composed of molybdenum or molybdenum-rich holes. Such molybdenum-rich holes, when you irradiate sunlight in presence of water, you create hydrogen peroxide. And this hydrogen peroxide destroys bacteria as well as viruses. You can see the destruction happening with very many spectroscopic and microscopic tools. Now, what you do is you create a column and you pass, and this column is now wound with a white light LED simulating white light. You take water with bacteria, pass it through this, and you see that the bacterial count goes down just with visible light. And that is because of this process I told you. So there can be a large number of phenomena of this kind. This is not an exhaustive list of phenomena, but many phenomena of this kind, atmospheric water harvesting or catalysis or purification or disinfection. With all of these, several different products have been put in the field. I told you about community water purification of this kind, but I did not tell you about something called capacitive deionization. We implement these for the removal of fluoride particularly. course, it can also remove arsenic and several others and salt. We also have atmospheric water harvesting with several different levels or several different capacities. Globally, there are several other efforts. For example, there are graphenic sheets, and using such graphenic sheets, there are people who engineer what are called porosity controlled sheets. It is possible that water can be flown in under certain conditions. Water flow can be stopped. The on and off can be controlled just by application of potentials. This is one thing that happens with a person called Rahul Nair in Manchester. Here in India, there are several people who create new materials. So, for example, this person, Professor Kanna Sureshan from IITM, is having this kind of materials. I hope this is going to play. There are several materials, normal materials that people have created. Let's say you have oil here and you added this material there. It picks up, these materials pick up water, pick up oil. And these materials or these advanced materials also pick up oil. And both are derived from cellulose. But Professor Kanna Sureshan has prepared these materials, and what you can see is that the entire oil can be picked up from here. But in this particular case, the parent material, you can't pick up the oil completely. So what it shows is that there are several advanced materials that are being produced. The kind of thing that Professor Sureshan does in Thiruvananthapuram is that such materials can be used for harvesting humidity. Well, it's not really harvesting humidity, harvesting fog. And this can also be used for collecting water. In our laboratory, we work on several other things, such as clathrate hydrates. Clathrate hydrates are cages of water with molecules such as methane trapped in them. So we showed in our one of these papers that clathrate hydrates, which generally are produced only at high pressure conditions, but can also be produced in low pressure conditions in the laboratory. But clathrate hydrates are very interesting. Although they are produced under the seabed, collecting in seawater, because there's a lot of methane produced under the ocean bed because of decaying organisms in the anaerobic conditions. And these methane at low temperatures and high pressures of water can produce water gas hydrates. They look like these, and people are interested in extracting this particular material from the ocean bed. You take these out, and when you come to the floor, shore, and then you extract gases from them. When you extract gases from them for your energy purposes, what is left behind is water, and that water is clean water, and the process is called hydrate-based desalination. You have, you get both water and energy in this process. In order to enable such kind of water purification or such technologies, advanced sensors are required. Very many sensors have been developed globally. So this is one such, wherein you can have a handheld electrochemical detector for contaminants in water. And this can, of course, be connected to mobile phones and subsequently to internet. A large number of such sensors looking at several contaminants is available. That data, imagine that every individual is collecting such data. That data on water quality in the country and elsewhere can create a platform wherein all of these technologies can be, all of these information can be displayed, and all of this can be used for additional benefits of improved water distribution, water-based decision-making, etc. Information for better decision-making, etc. So this is called hydroinformatics. And every state, we are trying to build such hydroinformatics platform. So this is one such proposed platform in the case of Punjab, where we can have water distribution, water quality, and water quantity, and it is possible to see this in a spatio-temporal fashion. Ultimately, all of this will go to something called a digital twin of water. You have physical water resources, but you can have a digital twin of these water resources. And therefore, water-based monitoring and distribution can be done far better. So we are doing this in a limited way currently with the data that are available from the state of Punjab. 7,000 locations water quality is measured, and we are showing these water quality changes, particularly in the context of arsenic, how it is distributed in the state of Punjab in a temporal fashion using data of the past 4 years. But then there is much more work to be done. In order to build water technologies for the world, we have built something called the International Center for Clean Water. This is at the IIT Madras Research Park. Anyone interested in clean water with an idea, they can come in, utilize the resources, and build a company. And this is at the IIT Madras Research Park, as I mentioned, with all facilities and resources provided. My science is done with students, mostly students. Some of them incubate also companies. And our technology in the context of water is called Amrit, anion and metal removal by Indian technology. And this is what has been implemented. Of course, water-related research, many people have contributed to that. These are all people who contributed to that. And our science is funded by the Department of Science and Technology with several startups and several state governments. IIT Madras is a very large place where very many people work in the area of water. We have been in a position to take such technologies to people just because there was tremendous support from this institution. So I must thank my director, Professor Bhaskar Ramurthy, and colleagues for supporting this initiative. Thank you very much. I'll be happy to take questions.
Thank you so much, sir. Thank you so much for such wonderful and informative lecture. Well, if you permit me, sir, I would like to take the liberty to ask you a few questions posted by our enthusiastic students in the chat box.
Absolutely. You're free to ask. I have, my screen is seen to you, observable?
Yes, sir.
Yeah, go ahead.
So, when you thought about this many years ago, was nanotechnology acceptable at the time? It might be a general question, but please answer it.
Yeah, very important. At that point in time, when I was looking at nanotechnology for clean water, many told me that this is probably not the right thing to do. You should look at nanotechnology in the context of better memory or better storage devices or better electronic properties, better magnetism and things of this kind. Water was considered as more mundane, and it was thought that this may not be the right direction to go. Yes, you are right. Many people were skeptical about it, but I decided to pursue that.
That's really so inspiring, sir. So, coming to the next question, it's not only about IITs or some other great institutes of excellence who does research. Their research does not have a direct connect with the people. There is some disconnection. So, how do you address this, sir?
Well, there is a disconnect. Society feels that institutions are in isolation. They don't contribute to people's problem. Institutions believe that it is impossible to address social challenges because institutions don't have the wherewithal to do this. There is no connection between the institutions and the marketplace. There is no way to create funding for such things. A PhD student doesn't feel that he or she can build a company. So there are very, very many reasons. You are absolutely right that there is a disconnect. But how do you address this disconnect? The way to address this disconnect is, one such example is what I just showed you. Every student who goes through this kind of a program also builds competence, also contributes to something or the other to address a real world challenge. So in that process is slow. You can't build suddenly you can't build an institution and say that every student who comes out of it will build companies. That is not possible. At least a reasonable number, 5%, 10% of the people, if they can contribute to something of this kind, gradually the institution will change, our society will change. It is happening today with this great initiative of Startup India and a lot of support in very many ways for startup, creating a startup ecosystem. And this is gradually happening in the country. Now, in specific areas, it may be easier. So, for example, in areas like information technology, it may be easier. But in several others, it may be very difficult. You are in the COVID era right now, but you can't immediately build, let us say, a COVID vaccine. This is, of course, very much needed, but it requires a completely different ecosystem. So there are areas wherein we can contribute to. There are areas which we may take much longer to contribute to, but we need to connect or create this social connect.
Thank you, sir. So next question is, what made you particularly to choose nanotechnology apart from all other? Like, what ignited you, sir, to choose this nanotechnology and this innovation?
Well, I have been working in this area for quite some time. This is one aspect. And so I have been a chemist. I continue to create new materials. I continue to create new chemistry. So this is one thing. And I look at the world as from a chemist perspective, everything is molecular for me. Everything looks like a molecule. Every problem looks like a molecular problem. So whether it is energy problem or water problem, I look at it as a molecular materials problem. And so it was natural for me to say that, well, there is an arsenic or a fluoride or mercury or uranium or something. The solution for that also has to be a chemical solution. So this is one aspect. Now, why did I choose nanotechnology? Is because I was seeing the power of materials in the nanoscale in addressing problems of this kind. So before looking at something like this, which I showed you in this lecture, before that, 2002, I was working on something called pesticides. So I showed that nanoparticles can be used to degrade pesticides. That was my very first patent in this area of clean water. And that really showed the power of nanomaterials in addressing several of these challenges. So therefore, I went on to look at nanomaterials in greater detail. But at that point in time, they were quite expensive nanomaterials, like those of gold and silver and things like that. A completely important switch, or very important switch, happened in my life and my research, that I decided that anything that I work on for water has to be down to earth, extremely cheap. And I looked at materials made with earth abundant elements. So I always looked at materials which are made with iron or silicon or things of this kind. They are all plenty. And that switch, nanomaterials with these elements, with affordability as an important criterion, made these technologies possible. Otherwise, all of these would have simply, been in the laboratory shelf and nobody would have used them.
That's really inspiring, sir. Your way of perception really inspired us. So moving on to the next question. Could nanotechnology be dangerous in future? As many people say, technology is killing nature. So can you please answer this?
I agree with you. Any technology can be used for good or bad. I chose this direction of clean water, and somebody else may choose another direction, leading to probably better explosives or things of that kind. Now, it is up to you. Science has no religion. Science doesn't say that it should be used for good or bad. It is with the user which direction to go. Now, coming to this question of toxicity or nanomaterials and their impact, I would say that these are aspects to be studied. So anytime when we implement a material, all the toxicity characteristics of such materials are studied, are evaluated, and only after approval, they are put in the field. And there are protocols that are available on this. And sometimes, if you don't know them, then that is a risk that is involved. Now, are there possibilities of unknown toxicity using such materials? Quite unlikely as far as these materials are concerned, because we evaluate in this context of clean water, we look at what are all the possible contaminants or possible species present in the purified water. And we ensure that this water conforms to all the international quality criteria. So therefore, there is no risk as far as this kind of materials and technologies are concerned, but there will be nanomaterials in general. I can't be making such statement, but you need to study them.
Thank you, sir. Thank you so much for being patient in answering all our questions. So now I hand over the lead to our faculty member, Dr. Shri ma'am, for vote of thanks.
Good evening, sir. Thank you, sir, for giving such a wonderful presentation. Definitely, it is encouraging to the students. And your presentation makes to realize the importance of the water purity and how to attain it by using the nanosciences or nanomaterials. And not only that, developing the smart water purifiers is definitely economical and reaching to the all areas in the world, actually. So thank you very much, sir. And hydro informatics interesting too. And that information is also. That is a very new area, I feel, because that is also very important. And thank you, sir, for making the students aware of all these new technology terms. Thank you, sir. Thank you for sharing your work.
Thank you very much. Please do share this recording. Ratnavali, please share this recording. Okay?
Sure, sir.
Thank you.
Thank you so much for this wonderful lecture, sir.
Thank you very much. Bye.
Bye, sir.